All right, so let's go with some questions from quiz 2. Okay, let's see. All right, the first question, the following peg diagram represents the mixing of two substances. It's a process. Which of the following statements is true about the two states involved? Okay. Now, what we know is the mixed state has a higher potential energy. That means weaker attractive interactions, and also it has a higher number of configurations than the unmixed state. Okay. Now, if you look at the options here, particles in the mixed state have stronger interactions. That is incorrect, because mixed state has a higher potential energy, meaning it has weaker interactions, weaker attractive interactions. So therefore, that option is not correct. Second option, particles in the mixed state have weaker attractive interactions and decreasing the temperature should fail. No, the thing is, if we have weaker attractive interactions, that means it has a higher potential energy, just like in this case. Higher potential energy states are favored at higher temperatures, not lower temperatures. So you need to increase the temperature to favor the mixed state. So option 2 is out as well. Particles in the mixed state have stronger, nope. Particles in the mixed state have weaker interactions, and increasing the temperature should favor the formation of the mixed state, and that I agree. All right, so moving on to the next question. Imagine you have a 25, okay, blah, blah, blah. Okay, you have the volume. Can we annotate? Let me see if we can annotate. Maybe not, that's okay. I think what I'm going to do is I'm going to take a screenshot and work on it. Okay, here we go. So we are given the volume, temperature, and pressure. Okay. What would the volume of the balloon be? So they're asking for V2. This is V1. B, if the temperature is increased to 6 times its initial value. So the T2, in other words, T2 is 6 times T1, and the pressure is also increased 3 times initial value. So P2, the final P2 is 3 times P1. Says P1. Okay. Now what we're going to do is we're going to write two equations. So we have P1, V1 is equal to number of particles times K Boltzmann constant times temperature. Okay, so we have T1 over here, and we know number of particles is not going to change because we are dealing with the same number of particles in the balance because we're not taking it out. Therefore, we can say that P1 V1 over T1, I just move the temperature to the other side, should be equal to a constant. Okay, now we can do that, or in simple terms, if you want to do it in algorithmic way, we can do this way as well. So this is the initial one. Let me call it equation 1, and then we can write the equation 2. In equation 2, the pressure is 3 times P1 now, and the volume is what we're finding, what we're trying to find, and then N is N, KB is constant. It's a constant. It's a constant, and then T temperature 2 is 6 times T1. This is our equation 2. Now, if we divide equation 2 by equation 1, all right, so we have 3P1, V2 on the left-hand side divided by P1 and V1. And on the other side, we have, I'm going to write the second equation part here now, and KB 6 times T1, divide this by N KB T1. Okay, now it's about canceling things out. P1 cancels out, N cancels out, KB cancels out. Okay, so that is T1 cancels out. Okay, and then what is left is on the left hand side we have 3 V2 over V1 is equal to, on the right hand side, we have just 6 in the numerator. Okay, that means our, so this is, that means our V2, the final volume is 6 times V1. I just moved my V1 to the right hand side, divided by 3, which is 2 times V1. So V1 is 25 liters, which is 2 times 25 is 50 liters. Okay, that should be your answer. So enter your numerical answer without units and with 2 decimal points. Okay, so let's stop right here. So we type 50 over here. Let's try it. 50 with 2 decimal points. Looks something like that. No units. And next page. All right. The vapor pressure curves for methanol, water, and isopropanol are shown below. Use the data to rank the strength of interactions amongst the particles of methanol. All right. Now we have water, vapor pressure curve at the bottom, and then isopropanol and the methanol at the top, meaning at any given temperature, okay, the water has the lowest vapor pressure, meaning it has strongest attractive interactions. Okay, so options A and B are out. Water, you know what? It leaves us with only option C. Okay, because in only option C we have the strongest attractive interactions for the water particles, or for the substance water. All right, for that reason it must be the answer. And then isopropanol and methanol has the weakest attractive interactions. How do we know that? Because at any given temperature, okay, look at any temperature, 300 or 310 or whatever the temperature you pick, okay, the methanol vapor pressure is much higher than that of water. Okay, so for that reason, the methanol has the weakest attractive interaction. So the correct answer is option C. Okay, moving on, select the PEG diagram for the following 2 conditions, A and B, of a mixture of different substances. All right, so it seems like oxygen mixing with water here. And then, you know what, let's take a picture and do it separately. All right, now let's think, what we want to do here is when we're trying to draw PEG diagrams, you know, think about the potential energy and the number of configurations separately. Okay, potential energy wise, we have a gas here where we have in state A, where we have particles far apart from each other, meaning weak attractive interactions. Meaning in A, you should have a higher potential energy than B. Okay, in B, the particles are closer to each other, meaning we have strong attractive interactions in B. All right, in option, when it comes to number of configurations, okay, when it comes to number of configurations, gases call the shots. So in state A, we have a higher number of configurations. Why? We have a gas there, which we don't have in state B. So number of configurations wise, A has a higher number of configurations than B. Okay, so A should be higher vertically. Okay, that means in the potential energy axis, it should be higher. That means it should be at the top. Okay, so these options are out. And also A should have a higher number of configurations. Okay, so that means it should be more towards right in the number of configurations axis. That should be option A, not C. So let's select, oh no, we cannot select here, but let's select option A and go to the next page. The vapor pressure curves for methanol, water, and isopropanol are shown below. Select the correct pressure and temperature values that would correspond to the submicroscopic representation shown below the graph. All right, here's the submicroscopic representation where isopropanol and methanol are in the gas phase. Okay, so just to remind us about what is involved here, okay, remember the vapor pressure curve is the liquid gas boundary of the phase diagram. Okay, this guy is the let me see, okay, I'm gonna do square here. So this is the vapor pressure curve, the liquid gas boundary. We know that above this curve, we have the liquid and below you have the gas. Okay, that's all you need to know here. Right? If all of my substances are in the gas phase, that means my conditions must be below all the lines. All right, so if you think about that, and we have methanol and isopropanol, right? We forget about water now, all right? As long as you are in anywhere in this region, okay, you will, the conditions satisfy the submicroscopic representation. That's the idea here. All right, now going back to our question, 15 kilopascals and temperature 300. Okay, 15 kilopascals and temperature 300 will put us just below the methanol curve. No, so that doesn't work. 25 kilopascals and 340. Yeah, that's nice. 25 and 340 will put us below the water curve even. We don't have to be below water, because water is not involved here. We just need to be below the gray curve. Yeah, so that works. Option 2. And let's look at the other ones as well. 25 and 320. 25 and 320 is just above the isopropanol. So isopropanol will be a liquid at that stage, so it doesn't work. 25 and 300 will be above the methanol curve. That means both methanol and isopropanol and water will be in the liquid, so that doesn't work. So the correct answer is 25 kilopascals and 340 Kelvin temperature, which is over here. That is option 2. Oops. Oh, option 2. Okay. Moving on, question 6. A tank containing propane, butane, and isobutane is at 5 atm and 25 degrees Celsius. Which of the following submicroscopic represent models best represent the tank under such conditions? So, okay, so let's take a picture and do it really quickly. Okay, so 5 atm and 25 degrees Celsius. 25 degrees Celsius in Kelvin is 298. Okay, so it should put us over here, something close to that. Okay, and then if that is the case, we are below the curve of propane. So propane is a gas. Okay, there's only one gas, and then both butane and isobutane should be in the liquid phase. So so option C is out because everything is the liquid phase there. Option B is out because everything is the gas phase there. And then in option A, I think the isobutane is a gas in option A. Okay, so we need propane to be a gas, not isobutane. So that is out. Therefore, that leaves us with option D. Is option D, we can see propane is in the gas phase because it's below the curve, and then butane is in the liquid phase, and also isobutane is in the liquid phase as well. So that is perfect. So option D is our correct answer. Right, that's D. All right, question 7. Different substances have different melting points because they have differences in intermolecular force strength or attractive interactions between the particles. And interact with forces of different strength. That's correct. That's the answer for that. Moving on to question 8. Okay, let's take a picture and do it maybe. Based on the image above representing a mixture at 298 Kelvin, select which statements are consistent with the particulate model of matter. Okay, assume nitrogen is 2O and C2Cl4 have different masses. You are told that H2O is the lightest, C2Cl4 is the heaviest, and then N2 must be in between. Anyway, so option 1, N2 is 2O and C2Cl4 have the same average kinetic energy. Yes. Same temperature means the same average kinetic energy per particle. Therefore, that is correct. Option 2, nitrogen molecules have the highest potential energy. Yeah, you know what? You can see that nitrogen particles, most of the nitrogen particles are in the gas phase. Actually, all of them are in the gas phase, meaning they have the weakest attractive interactions between the particles, meaning they have the highest average potential energy per particle. Therefore, that is true. Highest potential. Weaker the attractive interactions, the higher the potential energy. 2 is true as well. C2Cl4 molecules are moving at the lowest average speed. C2Cl4 is the heaviest. You are told that. Okay. So if they all have the same average kinetic energy, the heavier particles must be moving the slowest. That is correct too. All 1, 2, 3, 1, 2, and 3 are correct. Okay. And make sure that they're asking us to select the correct answers. Okay. That has to be the one. Are consistent. Okay, that's good. Question 9, which of the following graphs represents the change in the potential energy of the particles in the system when the substances undergoes the change corresponding to path 3? Okay. In path 3, we are going from liquid, this is liquid, and this is gas, liquid to a gas. Therefore, the potential energy must be increasing. Okay, so what is happening is with temperature, potential energy increases slightly. And then remember, we don't have delta PE here. So what we have is potential energy as it is. So they always start now, they're always negative. Okay, so we're going to start at a lower temperature. Okay, so we're going to say this. Okay, we're going to start at this temperature over here, which is lower, and this temperature is higher. Okay, so to read this diagram, let's say we need to start at a lower potential energy because we're starting at a liquid. All right, so let's do it needs to do something like this or this. Okay, because at lower temperatures you should have a lower potential energy. Therefore, options B and A are out because they are showing that at lower temperature you have a higher potential energy. So that's impossible. And then between C and D, you can see that in C, with temperature, potential energy increases, and then temperature increases, but the potential energy remains the same in this region. That is that is not possible, right? Because what happens at phase transitions is temperature remains constant, but the potential energy increases, like as in D. Okay, so for example, let's go to D. In D, you are increasing the temperature of the liquid, the potential energy slightly increases. That is this region over here. This is liquid. And then the liquid becomes a gas. During that, the temperature remains constant at the boiling temperature. But the potential energy increases a lot because interactions are weakened a lot. And then once everything is converted to gas, again, with temperature, potential energy increases slightly. And that is this region over here. So option D is the correct diagram here. All right, so D here is this guy. So we selected that. All right. Question 10, I think this is the last question. At pressure 70 kilopascals and temperature 310 Kelvin, decreasing the pressure at constant temperature will do what? All right, let's start that. 70 kilopascals and 310. 70 kilopascals and 310 is over here. You're decreasing the pressure at constant temperature, meaning you're decreasing the pressure. So that means you're going down vertically like this at the same temperature. Okay. So when you do that, what will happen? Decrease the average kinetic energy? No. If you're maintaining the same temperature, meaning the kinetic energy per particle should maintain the same, it should be constant. So this is incorrect. Decrease the average potential energy. Yeah, so because you see that above the curve we have a, no, actually we are increasing the potential energy. because above the curve we have a liquid and below the curve we have a gas. So if you go down the curve, if you cross that the boundary and then go down, then the liquid is becoming a gas, meaning you are increasing the potential energy. Decrease the average potential energy is incorrect. Increase the average potential energy is correct of the particles. So far, this is the correct answer. And last one, increase the average. No, you are not changing the kinetic energy at all. So the correct answer is option C over here. You are increasing the average potential energy per particle. All right, so let's select that and then submit the quiz. Yes. All right. That's how we do it. This is the way. I'll see you in class. Bye, everybody.